All right, so we're on page 3 of the 6.7 note packet. If you're following along, please do. You'll see method 3. We talked about graphing as a method where you graph each line, see where they cross. Method 2 is elimination method where you add the equations trying to get something to drop out by the addition or elimination method. Then the third method I promised you is called substitution. So substitution method says number 1, you will, step 1, solve one of the equations for one of the variables. If possible, solve for the variable that has a numerical coefficient of 1. Like for example, on number 13, this x has a numerical coefficient of 1, so does this y. This numerical coefficient is 2, and this one's negative 1, which any would be okay, but if it has a positive 1 in front of it, that's the easiest one to solve for. Then step 2, then substitute the expression that you found into the other equation, and then this yields an equation that's now solvable. So that'll get us going here. So we'll call this equation 1 and 2, and I'm going to decide to solve for this x variable right here. That's a 1x, and so I can easily solve for this x by throwing the y across the line and making that x equals negative y and a minus 4. So now it says x equals that quantity. So we're saying those are substitutable. They're equal to each other, so we can substitute one for the other for this x. So x is the same as negative y minus 4 in this system. So what we'll do, step 2, is we'll take this quantity that we got for x equals and sub it in for the x in the other equation. And this is just neat, it works. If you've never seen this before, you might be thinking, why? But it does, it works. We plug this in for that x, rewrite the equation 2 times, instead of x, it's substitutable, we said, for negative y minus 4 minus y equals negative 1. And then now we have a solvable equation. We can distribute the 2. And what I mean by solvable is before, in our system, we had 2 variables. I can't solve an equation as long as it has 2 variables. I can graph it, and it has multiple answers, but to get that one solution, you have to graph and see where they cross or use one of these methods. So now this is solvable just having one variable. Negative 2 minus y is negative 3y, and then minus 8. Take the negative 8 to the other side. Negative 3y equals 7. Dividing by negative 3, y is negative 7/3. Oh shoot, it's a fraction. So I'm going to double check my work and make sure, because I didn't think I started you out with a fraction. So let me double check here and see. So I had, you all check too. That one. So I solved for x by throwing this y across the line, made it, oh no, that's okay, negative y minus 4, thought I had it. And then I subbed that in for this x, kind of good to review the process. No, I think I'm good. I think everything's as it should be. I just thought I wouldn't start out with a fraction on you for your first example, so sorry about that. So yeah, the answer is negative 7/3. Which fractions happen? We've said that, but I try to avoid them, at least for the first example. Then you need to know what x is. So x is the negative of y minus 4. We can go right here, here, or here. We can plug it in to any of the former equations to find our answer. But the good thing about the substitution method is it has x solved for already. So x equals negative, now that we know y is negative 7/3 minus 4, and then we can do that on our calculator. That's going to be negative is positive. So negative, or positive 7/3 minus 4, and let's see, let me, like I said, sorry about the fraction. I didn't mean to do that to you on the first. By hand, you get negative 5/3. They're again like denominators, so the solution is, that's the x value in order. X is negative 5/3, y is negative 7/3. And that should be the solution to both of those equations when checked back in. Okay, example 2. I hope I made a better one on example 2 for you, or example 14, I guess it is. The next of this sort, number 14. Now number 14 is set up so well to use the addition method. That's what I would recommend if it just says use whatever method you want. if I added, those are already ready to add out, so it's set up perfectly for elimination addition. But we're practicing this substitution. So notice here, nothing has a coefficient of 1, so there's not going to be an easy way. So I definitely would not recommend this by substitution, but for a good practice of it, we will overcome this, right? But I definitely would do it with addition. So I'm sorry, I think I meant to make easier examples for us to start with. But for substitution, you solve for one of the variables, any of the 4 that you see. So I'm going to solve for this 2x, throw the 5y across the line, divide by 2, and then we have this quantity. Like I said, sorry, I don't think I meant to start with fractions, but that would be the idea. You solve for one of the variables, then you sub that into the other equation for this variable. These are interchangeable now. X is the same as. X equals that, so that means you can sub it into the equation for that variable. So we sub it into the other equation. You solve one equation for a variable, so I chose the first one and did that. Then I sub in what I got for that variable in the other equation. So -2 times what I got for x, write out the rest of that equation, and then solve that for your y. So notice, good thing here is the 2's cancel. It does leave a negative sign that needs distributed. So the negative sign distributes, makes 5y minus 7 plus 4y is 11. All right, so I've got 5y and 4y, which is 9y, minus 7 equals 1. It's a fraction again. 9y equals plus 7, which is 8. Dividing by 9, y equals 8 ninths. All right, and then we can find our x value just like we did on the other one by subbing it in where I said x equals -5y plus 7 over 2. So now that I know y is 8 ninths, we'll use our calculator for this. Plug that in your calculator and get your x value. That will be your x, y solution to that system. All right. Hopefully your examples you've got below are a little kinder to you. So pause the video. 15, 16, and 17 are working with the substitution method. Okay, number 15. 15 makes more sense in that it has one of the equation already solved for y. So if I saw it like that, I would say, hey, that's a good one for substitution method. It already has one of the variables y equals solve for, and so, you know, if I were going to do addition, I'd have to rearrange it and line the x's and y's up. So this is a good example of substitution. And it already has this helped out here that y equals that, so I can solve that, plug that in, use what they already solved for, plug that in for the y up here, and write x plus, instead of y, I sub in x plus 3 equals 5. Then that's solvable. 2x plus 3 equals 5. Throwing the 3 across the line, 2x equals 2. Much better here. X is 1. So the x value is 1, and I need its counterpart, the y value. So I take 1, plug it in for this x or this x. Either place will give you the solution. But notice right here is nice. 1 plus 3 is y equals 4. So now we have our x and our y solution, our ordered pair, that should solve both of those equations. Notice 1 plus 4 is 5, and 4 equals 1 plus 3 is also true. So that solution works. That's the consistent where they cross in one place. Nice solution. All right. What does it look like when we have a special case, though, in the substitution method? And we're going to see that here on 16. So 16 is also set up for use with the substitution method automatically. Y equals this. We can plug that directly in for that y and write it as x plus, instead of y, negative x plus 3, substitute it in for that, equals 5. Negative x and positive x cancels out, and you just have a false statement. In algebra, anytime you solve an equation and get a false statement, that means there's no solution. So those lines evidently were parallel. If we graph those, they run parallel to each other, and that's why there's no solution to that. All right, and then lastly, I bet we do the other situation that could occur. Let's see. We have x plus y equals 5, and y equals negative x plus 5. So again, this is set up perfectly for substitution. It has y already equal to a quantity. We plug that in for the y value right there because it's substitutable. Y is the same as. So for y, we substitute that in. And when we do that, this time the x's do cancel, but you're left with a true statement. We could even further go on and move the 5 over and have 0 equals 0 for that, which we know from our previous example means everything works. There's infinite solution. I guess not every possible point, but every point that's on one line is on the other line. They're lying on top of one another, so they're dependent system. We call this infinite. There's infinite solutions when you get a true statement here. If it's true, it's infinite. If it's false, like number 16, that means there's no solution. All right, we have one more thing to do, and I don't know if I can get it on this video or not. Let's try, see if we can add it in before we close out this section, is an application. It's called a break-even analysis. And so if you read along with me on page 4, it says, intersections of graphs arise in business in the context of a break-even analysis. In a typical situation, a manufacturer wishes to determine how many units of a certain commodity have to be sold for the total revenue to equal the total cost. The point at which the total revenue equals total cost is called a break-even point. If a manufacturer sells less than the number of units associated with that point, then they're going to lose money. If they sell more than that, then they're going to make money, a positive profit. So if you could represent your equations as y equals like your cost function, what it costs to do whatever you're selling, and y equals your revenue equation, then the break-even points when they equal each other, or when you graph them, where they cross. So it's just the same thing we were doing. That would be your break-even point where the graphs cross each other. So we have an example where we're selling a product that's $110 per unit. So that we're selling it for $110. So the revenue, the R of X equation will be $110 times each one of these little items. So whether it's a table, a dress, whatever kind of gadget it is, it's $110 selling times each one of those. That's the revenue we're bringing in. The cost, it says, is $60 for every item in cost, and then maybe the supplies to run the business or the electric bill, I don't know, the costs are $7,500. So we want to know, when does this equal this? What makes both of those true? Now when we graph a real application, sometimes it doesn't make sense to count by ones in your graphing. So these numbers are big, so it's going to be better to kind of maybe count by 50s or some bigger number. So we make a t-table for the first equation, 60x plus 7,500. Say y equals that. That's our cost equation. And it says in A part, plug in 50 units, 100 units, 150, and 200 and 250 to get some points. Plug that in for x. What if you sell 50 units? What is the cost? So I've done that, and I'll give you some points here. And see how these would be kind of hard to plot on just, if you counted by ones, you just have a hard time ever getting your graph big enough. So those are big numbers, so I'm probably going to count by even 1,000 here, or I think I counted by 5,000, but that's per your design. There's no exact right way to do this, but I'm going to count by 5,000s to graph this. Then when I do the revenue equation, it says plug in 50, 100, plug those same things in. So when I plugged in over here and I did an X and a Y, I came out with 10,500, 13,500, 16,500, 19,500, and 22,500. So to graph that, you'd plot those along, and you find out, I'm just going to kind of get this up here best I can with you. They do cross at a point, the intersection point, and it winds up being the point when X is 150 items. And we could have found that by the substitution elimination method as well, but at 150 items, they're making $16,500 in cost or revenue. So that is their break-even point, 150 items.